Now we look at inductors in DC circuits and the response to a square wave. So again, we can see here we've got a square wave that's being produced at the input. You can see the source here is shown as a square wave generator. But then as the circuit is conditioning that signal, you can see that the charge and discharge times rounds off those instantaneous transitions between high and low. So a good way to demonstrate both increasing and decreasing current in an RL circuit is to use a square wave voltage as the input. A square wave is a useful signal for observing the DC response to a circuit because it automatically provides on-off action similar to a switch. Now, please be aware, even though this is ideally shown as a square wave with these instantaneous transitions, if you pop those open and look at them on a no-scope, you'll see that they look more like what the bottom graph is showing anyway. So the time response will be covered in a future chapter, but when the square wave goes from its low level to its high level, the current in the circuit responds by exponentially rising to its final value. When the square wave returns to its zero level, the current in the circuit responds by exponentially decreasing to its zero value. So we're going to see how those time constants weigh in on a square wave across the input of a circuit. So we can see here in this example, we've got a dual switch operation here where we've got switch 1, switch 2, switch 1 open, switch 2 closed, 5-volt source, and a resistor and an inductor circuit. Let's look at an example. For the circuit shown, what is the current at 1/10 of a millisecond and at 6/10 of a millisecond? The RL time constant for the circuit then is calculated by using the values of the inductor and the resistor. 1 Henry, 10 k ohms gives us a 1/10 of a millisecond time constant. If the square wave generator period is long enough for the current to reach the maximum value of 5 time constants, the current will increase exponentially, and during each time constant interval will have a value equal to the percentage of the final current given in the table. So, so the current final is calculated using the relationship V source over the resistance. 2 volts, 10 k ohms gives us a quarter of a milliamp. The current at 1/10 of a millisecond then is, again, there's our figure, 0.63 or 63% of that total 0.25 or a quarter milliamp gives us 1.58 milliamps of current. So 158 thousandths of a milliamp. At 6/10 of a millisecond, then the square wave input has been at the zero level for 6/10 or 1 tau, 1 times constant, and the current decreases from the maximum value toward its final value of 0 by 63%. So again, we run it through the relationship. The current is equal to 1/4 of a milliamp. We're going to subtract that 63% of that quarter, and we get 0.092 or 92 milliamps, okay, 92 thousandths of a milliamp. Looking at voltages then in an RL circuit, when current changes in an inductor, a voltage is induced. Let's examine then what happens to the induced voltage across the inductor. Keep in mind that the generator produces a level that is like switching a DC source on and then puts an automatic low resistance ideal value of 0 path across the source when it returns to its 0 value. So we're going to place an ammeter in the circuit just like we've done before. The VL waveform is the voltage across the inductor, so V sub L. The square wave has just transitioned from 0 to its maximum value of 2.5 volts. In accordance with Lenz's law, a voltage is induced across the inductor that opposes this change as the magnetic field surrounding the inductor builds up. So if you need to go back to Lenz's law and familiarize yourself with that process. In accordance with Lenz's law, a voltage is induced across the inductor that opposes this change as the magnetic field surrounding the inductor builds up. There's no current in the circuit due to the equal but opposing voltages. As the magnetic field builds up, the induced voltage across the inductor will decrease and current is in the circuit. After one time constant, the induced voltage across the inductor has decreased to the 63%, which causes the current to decrease by 63% to 1.158 milliamps. This is shown in the figure. The voltage on the inductor continues to exponentially decrease to 0, at which point the current is limited only by the circuit resistance. Then the square wave goes back to 0 at a half a millisecond. Again, the voltage is induced across the inductor, opposing this change. This time, the polarity of the inductor voltage is reversed due to the collapsing magnetic field. Although the source voltage is 0, the collapsing magnetic field maintains current in the same direction until the current decreases to 0. Again, if you need to, go back and look at Lenz's law. So this is what was just described to you. You can see, as the current is flowing in the circuit here, you can see we end up with an input, output, input, output. What's happening here during this portion of the input waveform, you can see what's going on across the inductor. And so the inductor is decreasing down to 0. You can see where the source makes the transition to 0, and what we end up with is essentially a little square wave depiction here on the output. Induced voltages in an RL circuit, series RL circuit. You can look through this relationship, with the open and closing of the switches. What is happening? No current is flowing. No current is flowing. And then after the current starts to flow, you can see that the voltage across the resistor goes from 0 to 10 volts maximum. The voltage across the inductor goes to 0. So before the switch is closed, current 0. At the instant the switch is closed, V sub L is equal and opposite to the source. So we're at 10 volts opposite to the source. During the first 5 time constants, then the voltage across the resistor increases exponentially. There's your exponential curve with current, and V sub L then decreases exponentially, again obeying Lenz's law. After the first 5 time constants, V sub R is equal to 10 volts, V sub L goes to 0, and the current is at a constant maximum load. In this case, the voltage in the circuit as the inductor energizes, winding resistance is being ignored. Let's look at an example. The circuit shown has a square wave input, 10 volts. What's the highest frequency that can be used and still observe the complete waveform across the inductor? Assume the generator is set to a frequency determined in part A. Describe the voltage waveform across the resistor. So again, like we did before, let's calculate the time constant, L over R. 15 millihenries, 33 k ohms gives us a 0.454 microsecond time constant. Okay, the period needs to be 10 times longer than tau, the time constant, to observe the entire waveform. So T is equal to 10 times tau, which is 4.54 microseconds. We know that the inverse relationship exists between time and frequency. So if we invert that 4.54 microseconds, we end up with 220 kilohertz as the frequency. The voltage across the resistor has the same shape as the current output. The general shape was shown in figure 1324 and has a maximum value of 10 volts, the same as V source. So when we come back, we'll take a look at the exponential formulas that help us to determine V and I at times that are set up by our time constant.